Let's take a look at an application problem where we have a model for vertical motion. This is when an object is fired or thrown just straight up in the air and it flies up, reaches a maximum height, and then drops back down. It's really going straight up and straight down, so there's no x component whatsoever, but instead we use the x-axis to represent time. So we can visualize this object, let me zoom out, starting from its position here at, and this is in meters for this example, 25 meters above ground. It's thrown up, and as time goes on, it reaches its maximum height here after about 1 second, and then falls to the ground, landing in about 3.5 seconds. In this video, I'll cover the 3 different models for parabolic motion or quadratic functions. The standard model shows a standard form that's at squared plus bt plus c, thinking of just the standard coefficients. But what I've done is swap these out for the values that contextualize the problem for vertical motion. This relationship is explained very well in calculus. We call this Newtonian physics, or Newton's laws of gravity and motion. In this first term, we're representing the acceleration due to gravity, and its effect is downward, so that's a negative pull of 1/2 times this gravity acceleration. So I've used 9.81 meters per second squared for the metric system. We could also do 32 feet per second squared to use English units. And then we have an initial velocity that is proportional to how much time is spent. You could kind of think of it as we have an initial velocity headed upward, and we're shedding off that velocity, slowing and slowing because of this gravity effect here. And then at a certain point, those cancel out and we sort of reach our peak and fall to the ground. Now this last piece is an initial height. We could remove that or set it to 0 and throw it straight up from the ground. Here I had it at 25 meters. And that just shifts us up and down, which we'll see with that vertex model is really just a vertical shift. Now the standard model is really most important to arrange the inputs. A lot of times the standard model doesn't tell us much information when it's not a contextualized problem. Say it's just 2x squared plus 5x minus 9. We don't really learn a lot from that. However, when we're arranging this initially, we use this standard model because it is really the true relationship between all of the variables at play in this kind of problem. So you could try it out using different inputs. This first one for Earth would only be 9.81 or 32, depending on if we're using meters or feet. Although if you wanted to look at projectile motion on the moon, for example, you could do about 1/6 of that and see how that changes things as well. Next, we'll look at the vertex model, and I'll first just show you that we have the same graph here when I toggle this. And before I do that, I'm going to actually add a couple points to the standard model, which will help me to center this a little bit better. So I'm going to use this I'm going to use this edit list and create a table for the function. Just for some key points, -2 to 2, we see that those aren't really necessarily the best points, but what it will do is, let me hit this plus button here, and it rescales the axes. You see we don't have the same scale anymore. We have 1, 2, 3 seconds on the t-axis, or the horizontal, and this vertical axis is 20 meters, 40 meters, and up. So that's a nice quick way to scale these and really make your graph visible in a great way. You could always delete it after that, and you can check in this graph settings area to really have a more fine-tuned approach to that. The other thing I might do here, if I really want to improve my documentation of the problem, is I would call this t seconds, and I would call this one maybe y in meters. Or you could have h, or you could have something else. But I'm going to stick to usually we do x, y. I'm going to stick to ty because I think that will be the most standard. Now when I move down to vertex, I'm actually going to use these points to talk about the concept of transformations of functions. And so just to go through what we see here, there's only 3 variables. I've defined a as the leading coefficient just by going back to the previous problem and really just typing that in. So a is negative 1/2 g from the previous, and we can always do that on paper too. Whatever that leading coefficient is in standard form, it's still going to be the case in vertex form. The next thing I have is my h. So t minus h represents a horizontal shift. We're really thinking about where is the vertex, or in this case, the top of this parabola that's pointed downward. And that's always happening at negative b over 2a. That's always going to be sort of our little shortcut to find that. So b, I'm just recalling from before, the b coefficient is actually called v subscript 0 for initial velocity, velocity at time 0. Now it's really pulling from that variable below. And lastly, k, it's pulling from this, which is really just the height at that vertex. So if I plug h into the function, I'm using f1 that I defined in the standard model. I can't use f2 because it doesn't have all its variables yet. So you have to use the previous result, otherwise you get kind of a circular loop here. If I change that to 2, you'd say you can't define these two things in terms of each other. So if you get into coding, this is really something you have to really be careful of. You always need to reference something previous in the new results to avoid creating that circular assignment. And now let's look at the concept of transformations with this vertex model. Again, I will edit my list and add a table that's attached to that function, which is really nice just because it's already inputting the values we want. We have kind of a standard set of inputs from -2 to 2, increments of 1. However, we recognize that this is being shifted, and maybe we want to visualize what that shift looks like. So if we recognize that we're shifting it h to the right, then we can actually go up here and just add an h to each of these inputs and represent that right shift for the inputs, and everything else will follow on its own. So basically, as long as we're putting in a shifted input, it will then do all the stretching and vertical shifting. And so, for example, let's look at this center point. If we really want to see sort of the path that this point takes through transformations, we should add a parent function or reference function here. I'll just call it f of t. Will it let me do that? Yeah, I don't have an f yet, so my f of t will just be t squared as my reference function. Then I can add some key points to the list like I've done before. And there we see my initial 3 points, which we recognize from the quadratic function. We might be more used to seeing it like this. When we center that, we can see our standard parabola here. But now we're trying to see how that got translated into what we see here as a blue dashed line. It is flipped, moved, and stretched. So looking at the center point, we see that we're shifting it to the right by h, with h having a value of roughly 1. So we can see that path to the right. We have a k where the point is moving up, and in this case it's about 30 meters. So it went to the right 1 and up 30, and we see that's how we get to that vertex here. The other transformations that we have is a flip, and that's happening with a negative value for my a. It's a vertical flip. And lastly, the 1/2 g was half of 9.8, so about 4.9 as a vertical stretch factor, meaning that the best way I can explain it is if we look back at the original, our initial move was over 1, up 1. So we think about kind of like an average rate of change. We went over 1, up 1. That's about a slope of 1. But that slope is changing as I go because it's a curve, not a line. The next sort of differential that we have is we go over 2. Let's start back from the beginning here. Over 2 and up 4. So then we'll go over 3 and up 9, for example. So that sort of over and up is getting stretched vertically, meaning that the first time we go over 1, instead of going up, or in this case down by 1, we're going to go down by 4.9 times that amount, and 4.9 times the next amount, and the next amount. So let's center our blue dashed line and take a look. If I go over by 1 second, so from about 1 to 2 seconds here, then the y differential, the y change, is about 4.9. We can see that, 30 here to 25.1. It's a little bit off because we got some more decimals there. From the vertex, the next move that I do is over 2. And instead of going a distance of 4 vertically, so that's 2 squared to get 4, we'll do 4.9 times 4. I would just round it off to 5. 5 times 4, that's going to give us about a distance of 20. So from 30 down to about 10 we see there for our y values, we got that stretch. So you just think of starting at the vertex, going to the left and right. Normally it's an up or down by 1, but we're stretching that times 4.9. The positive keeps it this way, the negative flips it down this way. It's just a little run through of those transformations of a function to sort of help see a equation and form a mental image of what it looks like, which I know is easier for some than others. Now I'm going to hide this vertex model. I think I'll also get rid of, well, I can leave those points because that actually helps me sort of center my graph there. Now we'll move on to factored form. Factored form is best for us to model the zeros. I've used the quadratic formula to find t1 and t2, which are the two zeros of the original function. You can check out here, we have negative b. B is that middle coefficient, plus or minus in front of the square root. The square root inside is called the discriminant. That's b squared minus 4ac. Just swapping out a v0 for b and a y0 for c. And all I did was typed it once and then copy and pasted it to change it with a plus minus. And now this factored form is very easy to fill in. We already have the same a, that stays consistent throughout, and then it's t minus each root or each zero, depending on what terminology you're using there. And this, we don't necessarily learn a lot other than we learn the zeros from this model, which is something that we didn't inherently have sort of baked into these other models. So the factor model is really all about seeing the zeros as we write the equation, having those very visible. And if I wrote this on paper, I might even round and put in negative 1.46 and 3.50 into those positions for T1 and T2.